For how many real numbers x is between 0 and 10 is x squared plus the fractional part of x an integer. And we're given that the fractional part of x is equal to x minus the greatest integer that is less than or equal to x. So we can also write x squared plus the fractional part of x. Using our definition, it's equal to x squared plus x minus the floor of x, which is the greatest integer function. And this is an integer, we use that symbol, if and only if x squared plus x is itself an integer. Why? Because the floor of x is defined to be an integer. So it remains to find the number of values of x between 0 and 10 for which x squared plus x is an integer. And to do that, we need to find the minimum and maximum values of x squared plus x for x between 0 and 10. And we can confirm that on the interval 0 to 10, the function x squared plus x is a strictly increasing function by using d over dx. We know that d over dx of x squared plus x is equal to 2x plus 1. And that's greater than 0 if and only if x is greater than negative 1/2. That's lower than any value in the interval 0 to 10. So on that interval, x squared plus x is always increasing. So the minimum will occur at 0 and the maximum will occur at 10. The minimum is just 0, and the maximum is 10 squared plus 10, which is equal to 110. And because this function x squared plus x is strictly increasing on the interval 0 to 10, each integer between 0 and 110 is going to be obtained by x squared plus x exactly once for x between 0 and 10. So, for example, 72 is only achieved when x equals 8. No other x can give you 72. So, the number of real numbers x between 0 and 10 for which x squared plus x is an integer is simply the number of integers between 0 and 110, and that's equal to 111. Let ABCD be a convex quadrilateral with AB equals BC equals 1 and CD equals 2. If the perpendicular bisectors of AB, BC, and CD all intersect at the midpoint of DA, then what is the length of side DA? So we have a convex quadrilateral ABCD with AB equals 1, BC equals 1, and CD equals 2. And it is given that the perpendicular bisectors of AB, BC, and CD all intersect on the midpoint of DA, which is here. I'll call that M. So the perpendicular bisector of AB, BC, and CD all intersect at the midpoint of DA, which is M. Well, if the perpendicular bisector of a segment passes through a point, and we know the distance from that point to one of the endpoints of the line segment, the distance to the other endpoint is also the same thing, because it's on the perpendicular bisector. It's the set of all points that are equidistant from the two endpoints of a line segment. And M lies on all three perpendicular bisectors. So we know that MA equals MB, MB equals MC, and MC equals MD. Let's call that common length R. So now we know that R is the radius of a circle centered at M that passes through A, B, C, and D. So in fact, quadrilateral ABCD is actually cyclic with diameter AD. Let's draw in that circle. So now we know that quadrilateral ABCD is actually cyclic. We can use Ptolemy's theorem on quadrilateral ABCD. It says that the sum of the products of opposite sides is equal to the product of the diagonals of quadrilateral ABCD. And since AD is the diameter, both angles ABD and ACD are right angles. So we can get the lengths of AC and BD using the Pythagorean theorem. AC is just the square root of 2r squared minus 2 squared, which is the square root of 4r squared minus 4. And BD is just the square root of 2r squared minus 1 squared. Because triangle ABD is a right triangle. So now we can use Ptolemy's theorem on quadrilateral ABCD. We get 1 times 2r plus 2 times 1 equals the square root of 4r squared minus 4 times 4r squared minus 1. And now we can square both sides. we get that 2r plus 2 squared equals 4r squared minus 4 times 4r squared minus 1. So 4r squared plus 8r plus 4 equals 16r to the 4th minus 20r squared plus 4. And now we can cancel the 4's. So we have 16r to the 4th minus 20r squared equals 4r squared plus 8r. 16r to the 4th minus 24r squared minus 8r equals 0. We can divide by 8r to get 2r cubed minus 3r minus 1 equals 0. Now, you might have already noticed that minus 1 is a solution to this cubic in r, because minus 2 plus 3 minus 1 is equal to 0. So r equals minus 1 is a solution to this cubic. So we can divide by r plus 1. It means r plus 1 is a factor, so we can divide. Let's divide r plus 1 into 2r cubed plus 0r squared minus 3r minus 1. Make sure to write all the coefficients when you do long division. Okay, so r plus 1, we multiply by 2r squared. That gets us 2r cubed plus 2r squared. That leaves us with negative 2r squared here. So we write 2r squared minus 3r. Multiplying by negative 2r will give us negative 2r squared minus 2r. So we write minus 2r. And then the difference here is negative r. Then we bring down minus 1. And that's exactly equal to r plus 1 times negative 1. So we write minus 1 here. So 2r squared minus 2r minus 1 is the quadratic we need to solve that r satisfies. It can't be negative 1 because r can't be negative. So r is a solution to 2r squared minus 2r minus 1 equals 0. We can use the quadratic formula to solve this, or we can just divide by 2. R squared minus r minus 1/2 equals 0, which is r minus 1/2 squared would be r squared minus r plus 1/4. But this is 3/4 less than that. So it's r minus 1/2 squared minus 3/4 equals 0. We have r minus 1/2 equals root 3 over 2. R equals root 3 plus 1 over 2. But we want the length of side dA, which is 2r, and that's equal to root 3 plus 1, which is answer choice E. How many ordered octuples A1 through A8 are there such that each AI is either 0 or 1 for all I between 1 and 8, and A1, A2 plus A2, A3 plus A3, A4 plus all the way up to A7, A8 equals 0. So we want each AI to equal either 0 or 1, and this product sum, A1, A2 plus A2, A3 plus A3, A4 plus all the way up to A7, A8 is equal to 0. That means we can never have a 1 as the product of two consecutive AIs here. Because if we did, then we'd need a negative number to counter that in a different product. And that's not possible because each AI is either 0 or 1. So we need all 7 of these products to be equal to 0. The only time it's equal to 1 is if both of the consecutive AIs are equal to 1. And we want that to never happen. So the problem is asking, if there are any 1s at all in A1 through A8, how many ordered octuples are there in which the 1s never appear in consecutive positions? They have to be separated by zeros. So let's write the zeros first. It's clear that there are at least 4. Because if there were less than 4, there'd be more than 4 1s, and 2 of the 1s would have to be consecutive. So let's start with the least case, which is 4. Then the 1s have to go in these places, and any arrangement will work if the 1s are separated by zeros, obviously. So for example, we could have this, where the 1s appear in positions 1, 3, 5, and 8, and they are separated by zeros. If there are 4 zeros, there have to be 4 1s. And there are 5 places in which we can put the 1s. So the number of ways we can do this, if there are 4 zeros, is 5 choose 4, which is equal to 5. Now, if there are 5 zeros and 3 1s, then we have to put the 3 ones in these 6 spaces. For example, this can work. The ordered octuple A1, A2, A3, A4, A5, A6, A7, A8 is equal to 1, 0, 0, 1, 0, 0, 0, 1. That works for the sum of the products being equal to 0 because each one is separated by zeros. And we have 6 spaces to put 3 of the ones. So that's 6 choose 3, which is equal to 20. You could have put the ones anywhere from among these 6 spaces. The same is true for our next case. If we have 6 zeros, then we need to place 2 ones in these 7 spaces. For example, this could work. So we have 7 choose 2 equals 21. And we can go on for 8 and 9. It would be 8 choose 1, which is 8, and 9 choose 0, which is 1. That would be the case where all of the entries are zeros. So we can sum these up, and that's the number of ordered octuples A1 through A8, such that each AI is either 0 or 1, and the sum of these 7 products is equal to 0. So that's 5 plus 20, which is 25, plus 21 is 46, plus 8 is 54, plus 1 is 55, and that is equal to answer choice D. Let P of x be a polynomial of degree 7 with P of k equals 1 for all integers k between -3 and 3. If the coefficient of x in P of x is equal to the constant term in P of x, then what is the value of the modulus of P of 4? So we're given that P of k is equal to 1 for all integers k between -3 and 3. So we should define a new polynomial Q of x, which is equal to P of x minus 1. And that polynomial Q of x would have roots at all the integers, -3 through 3. So we have Q of x equals P of x minus 1, which would be equal to A times x plus 3 for the -3, x plus 2, x plus 1, times x minus 1, times x minus 2, times x minus 3, for some constant A. And then P of x, we can do A times all this stuff, plus 1. So now we have that the coefficient of x in P of x is equal to the constant term in P of x. The constant term in P of x is just 1, because everything else has an x in it. So we can write that the coefficient of x to the 0 in P of x, which is just the constant term, is equal to 1. The coefficient of x in P of x is equal to A times plus 3 times plus 2 times plus 1 times -1 times -2 times -3, which is equal to A times -9 times -4 times -1. And that's equal to -36A. So now we can set the two equal. We have 1 equals -36A, and so A equals -1 over 36. And now, plugging that back in to our equation for P of x, which is A times x plus 3 and all that stuff, we have -1 over 36. P of x equals -1 over 36 times x plus 3 times x plus 2 times x plus 1 times all the way down to x minus 3 plus 1. And now if we were to apply this on x equals 4, since that's what's the question asking for, we would get that P of 4 is equal to -1 over 36 times 7 times 6 times 5 times all the way down to 1, which is just 7 factorial plus 1. And so 7 factorial is equal to 5,040, and 5,040 over 36 is just 140. So we have -140 plus 1, which is equal to -139. And the modulus of -139 is 139, and that's equal to answer choice B. For a positive integer n, let d1 equals 1, d2, d3, in ascending order up to dk equals n, be all of its positive divisors. How many positive integers n between 2 and 100 satisfy the property that di plus 1 minus di over d2 minus d1 is an integer for all I between 1 and k minus 1? So we have d1 equals 1. That's always true because 1 is always the smallest positive divisor of any integer, n. And then d2 is the smallest prime that divides n. Let's call it p. Because assume not and d2 weren't prime, then there would be other divisors of d2 between 1 and itself. But we're assuming d2 is the second smallest divisor of n other than 1. So there's not really going to be any other divisors besides 1 and d2 itself. If there were, they would also appear on the divisor list of n. So d2 is prime, and it's the smallest prime that divides n. So with that in mind, let's rewrite this fraction di plus 1 minus di over d2 minus d1. Assuming that d2 equals p, the smallest prime that divides n. We have di plus 1 minus di over p minus 1 is an integer. So we have di plus 1 minus di is congruent to 0 mod p minus 1. And if we use I equals 2 for this, then we get that d3 minus p is congruent to 0 mod p minus 1. And that implies that d3 is congruent to 1 mod p minus 1. And now if we use I equals 3, then we can get d4 minus d3 is congruent to 0 mod d2 minus d1, which is just p minus 1. But we know that d3 is congruent to 1, so we have that d4 is also congruent to 1 mod p minus 1. If we keep doing this for all divisors of n, we'll see that all of them are congruent to 1 mod p minus 1. So we can write that all di are congruent to 1 mod p minus 1. So now let's do casework based on the smallest prime that divides n. And obviously if n is prime itself, there's nothing to consider here. We only have to take one ratio, which is d2 minus d1 over d2 minus d1. And that's always an integer, it's 1. Otherwise, let's do casework based on the smallest prime that divides n. So we have, if p equals 2, then di is congruent to 1 mod 1. That's the same as saying it's an integer, which is always true. If p equals 3, then all of the divisors of n are congruent to 1 mod 2. That means they're odd. But since the second smallest divisor of n is equal to 3, that means 2 didn't appear. So it's not even. So we have to have n is odd, and all of the divisors of n are odd, and therefore they are congruent to 1 mod 2. That's always true. So I think it would be better to focus on the cases that don't work instead of those that do. And we're going to do that with p equals 5. So in order for a positive integer n to work, we must have that all of the divisors of n, where p equals 5, are congruent to 1 mod 4. And obviously, if n was the product of 3 different primes, we'd have like 5 times 7 times 11, which is 385. That's way above the requested range of n is between 2 and 100. So we only have to consider when n is the product of 2 different primes. All of the divisors of n are congruent to 1 mod 4. When is that not true? I mean, it's not true when the third divisor is not congruent to 1 mod 4, but it is still prime. So we don't have this property when d3 is equal to 11, because that's not congruent to 1 mod 4. And we don't have this property even when it's equal to 7. It's not there. It's not there when it's equal to 11, and it's not true when it's equal to 19. So 5 times 7, 35, 5 times 11, 55, and 95 all do not satisfy the property that this ratio is an integer. Those are the only ones we have found that are less than 100, or less than or equal to 100. And if p equals 7, then we need that all of the divisors are congruent to 1 mod 6. But this is not true when the third divisor of n is equal to 11. And that's literally it, because 13 works. 17 is too high, but it wouldn't work. 7 times 17 is equal to 119, which is greater than 100. So 11 is the only value of D3 that we have n is less than or equal to 100. But still, D3 is not congruent to 1 mod 6, and so the condition is not satisfied. 11 minus 7 over 7 minus 1 is not an integer for n equals 77. So we only have 4 values of n between 2 and 100 that do not satisfy this condition. There are 99 possible values of n, and 4 do not work. So the answer is 99 minus 4, and that's equal to E, 95. Thank you for watching my YouTube video, and please follow my channel if you would like to see more videos and you would like to prepare for the AMC 12A on Wednesday, November 8th.